Okay, so this screencast is about domain and range and also the next section, section 1.3. We started this in yesterday's video. We talked about sets of numbers and intervals. So I'm going to jump right into what domain and range are. Both of these terms pertain to functions, and the domain of a function is the set of allowable input numbers for the function. Now, you might think, well, why would a number not be allowable as an input? And there are a number of reasons. Here's a real simple example just to start, and we'll see some other examples as we go. If we take this function, 1 over x minus 2, the number 2 is not an allowable input, because if I try to evaluate f of 2, I'm going to get 1 over 0, 1 over 2 minus 2. And 1 over 0 doesn't mean anything. It doesn't make any sense. You can't have 0 in a denominator. So the point of this is just to illustrate that this isn't a trivial notion. There is something here. There are some functions where there are some numbers that aren't allowable as inputs. And again, we'll go into a little more detail soon. So the domain is a set of inputs, the allowable set of inputs. The range is a set of outputs. It's the set of outputs that the function is capable of producing, the set of output numbers that have an input number mapped to them. And again, not every function can produce any conceivable number as an output. And here's a simple example. Oops. If we take the function f of x equals x squared, the number -4 is not in the range because I can never produce that as an output. I can't plug something into this function, square it, and get -4, because when you square something, you'll never get a negative number. So again, there is something to this. It's not the case that for any function you can plug in anything. The domain might be restricted. And it's not the case that for any function you can produce any output. The range might be restricted as well. Okay, so let's look at some examples. One way that domain and range can be restricted is by context. If your function models something, then the quantities in the model might be restricted in their values somehow. So for example, suppose that I have a function modeling the population of a small town. And I have only a couple of data points here. In 1960, there were 100 people in this tiny town. And then 50 years later, it has grown to 1,400 people. So first, in terms of modeling the situation here, in this class, when we model things, we'll always model them with functions, which means we have an input variable and we have an output variable, and we have some function that connects the two. Here, the two quantities are the year and the population of the town. And so we'll model this by thinking of one of those as the input and one of those as the output. This is a little subjective, but I think that the only reasonable way to do this is to think of population as an output from year. That is, the population is a function of year. So we'll call the input variable t. That's a popular choice for the time variable. Of course, the letter you use doesn't really matter. And we'll count number of years from 1960. So that's our input variable. And then the output variable is the population p, right? So here's my output. Here's my input. All this is just sort of modeling the situation mathematically. And so the domain of this function is the set of allowable inputs. Well, I only have information from 1960 to 2010. Now notice that t is the number of years since 1960. So the domain is not 1960 to 2010. Rather, when the year is 1960, the value of t is 0, because that's 0 years since 1960. And when the year is 2010, the value of t is 50, because that's 50 years since 1960. So the domain here is the interval 0 to 50, and this is sort of specified by the context of the problem. As far as the range, we're going to have to make a little assumption here about the situation. And the assumption I'm going to make is that the town's population grows steadily. So it grows from 100 up to 1,400, and it never jumps out of that range. Now, if we had more information, then we might modify the range appropriately. But under that assumption, our range here is the set from 100 to 1,400. So one way that domains and ranges can be restricted or determined is based on the context of the problem and what the variables mean. Let's look at a couple of other examples. Let's find this one in the text. So example 4, I'm pulling from the textbook. It is, where is it? Oh, here it is up here. Right, so this is just from the textbook. It's on, I think, page 26. And here I have the graph of a function. And I know it's a function because it passes a vertical line test. I can't draw a vertical line that hits this in more than one place. The input is on the horizontal axis, right? So the input is the year. And the output is on the vertical axis. And you can tell from the label that the output is thousands of barrels of oil per day. Those are the units at any rate that the output is measured. So the domain is the set of allowable input values. Well, the input range here goes from the left, far left here, which is what, about 1975, to the far right, which looks like 2008 or so. Yes, I think that's right, because these little lines here are marking off years. So let's see if I got that right. Yes, so 1975 to 2008 is the domain. The range of, where we go? Here we go. The range of the function is the set of outputs that it can produce. Outputs are on the vertical axis, and you can see the output range goes from this low value where my cursor is. So that's maybe a little below 200, call it 190 or so. And this right up here where the cursor is now is the largest output value, and that's a little more than 2000, I guess, maybe 2010-ish. So we have to estimate a little bit, but my best guess at the range is, again, the interval from 190 to 2000. And recall that this is interval notation, right? So this expresses the set of all numbers between 190 and 2000. Another example from the textbook, I'm just going to scroll forward to this one, very similar example, right? So here, again, this is a function. It passes a vertical line test. The inputs are on the horizontal axis. Again, years are the inputs. And the outputs here is, this looks like the increase in world population measured in millions of people. So the way to interpret this is down here in what looks like about 1950, maybe 1951. In that year, the world population increased by about 45 million people, and so forth. So again, the domain is the input range. So that is, I guess I get, again, about 1951 or 1952, out to, I guess that's about 2003 or 2004. So again, let's see how we did here. Yeah, that's about right. And then the range is the output range. So the outputs go from a minimum here of about 40 million to a maximum over here, I think, of about a little less than 90, right? So maybe 88 or 87 million. So my range is the interval from 40 to 88, right? Notice that domains and ranges are sets of numbers. So in answer to the question, what is the domain? The response should be some set of numbers. All right, so we've been talking about domains and ranges from graphs and from context. If you have a formula for a function, there are algebraic restrictions on domains sometimes as well. And there are two that we have to be concerned with right now. We'll encounter another one later on in the course. The first restriction comes from the fact that denominators can't be zero. You can't divide by zero. And so if a function has an input variable in a denominator, then you may have a domain restriction, right? So this function, for example, the function 1 over x, has the input variable in the denominator. Denominators can't be zero. So the domain of this function is, let's read this thing slowly, the set of all inputs x, right? So I've read the blue part so far. The colon gets read as a such that, so this is the set of all inputs x such that. What's the restriction? Whatever is in the denominator cannot be zero. So in this case, that is x. So the domain of this function is almost all real numbers. There's just one thing left out, and that's the number 0. Here's another example of the same phenomenon. Here is a more complicated function. Again, though, we have an input variable in the denominator. You can see the x down there in the denominator. So there's going to be potentially a domain restriction. What is the domain? It's the set of all x such that, right? So I've just read the blue part. What is the requirement? Whatever is in the denominator can't be 0. So what's in the denominator here is not just x, but 3x minus 7. So that's what is not equal to 0. And then we can solve this inequality the same way we would solve an equation. Just add 7 to both sides and you get this inequality, and then divide both sides by 3 and you get this inequality. And this is really the best way to report your answer, because I can tell immediately what the restriction is. Looking at this set, it's not immediately clear. So what value of the input is prohibited? Well, it's 7/3 is not in the domain of this function. The other domain restriction that we need to worry about right now are square roots. You can't take the square root of a negative number. Again, we only work in the real numbers, and that's why this is the case. So if your function has the input variable under a square root, and the simplest example is just the square root function, f of x equals the square root of x, then potentially there's a domain restriction. The domain of a function like this is the set of all numbers x such that, again, that's the blue part. What's the restriction? Whatever is under the square root has to be greater than or equal to 0. In this case, that's just x. So it's just the set of all x such that x is greater than or equal to 0. Notice in this case that this set is pretty easy to express as an interval, right? It's the interval from 0 to infinity. And notice also that 0 is included. You can take the square root of 0, you just can't take the square root of anything that's less than 0. All right, a slightly more complicated example, I think, is here. So again, I have a function where there's an input variable under the square root. You can see the x right there underneath the square root. So what's the domain restriction? Well, the domain here is the set of all x such that the restriction is that whatever's under the square root has to be greater than or equal to 0. So in this case, that's 4x plus 12 that has to be greater than or equal to 0. And once again, we get an inequality here that we can solve just using some basic algebra. So I subtract 12 from both sides, then I divide by 4, and I get to this simplified version of the domain, the set of all x such that x is greater than or equal to -3, which again I can express in interval notation. So this function g, for example, is not defined at x equals -4 because that's not in the domain. It is defined at 5 because that is in the domain, and so forth. Ranges are more difficult to figure out algebraically, and we won't worry about that for the moment. You should be able to figure out ranges from graphs and contexts, but algebraically, we'll just worry about figuring out domains. If a function has neither of these restrictions, that is, if a function is defined algebraically, here's an example, h of x equals 5x minus 9. There's no denominators, there's no square roots, then our default will be that the domain is everything. That is, we will assume that any input is quote unquote allowable unless there's some good reason not to allow it. And this is a perfectly good way to express that. The domain is all real numbers, or you can use that fancy double struck R and say the domain is the set of real numbers, either way. So from graphs, we talked about this a little bit in the 2 examples up above, but real quickly, here again, I have the graph of a function, passes a vertical line test. What's the domain? It's just the input range, which goes from, looks like -2 to +4. And the range is the output range. So that goes from down here, that looks about like -7 up to +5. So I think we have that down here. Indeed, right? So the domain is the interval from -2 to 4, and the range is from 6 to 5. A similar example, you'll notice one little sort of quirk in this graph is this open circle over on the right-hand side. There's some question when looking at a graph like this as to whether this endpoint is included in the graph or not. And so the way that we'll try to communicate that as we did with line graphs, is we'll use a closed circle to indicate the endpoint is included and an open circle to indicate that it is not included. So here I have 2 closed circles, right, at both ends. And that's why I'm using square braces here for the domain and range, because those endpoints are included. Here, I'm going to have one endpoint included, the other endpoint not included. So the domain here is the input range. The leftmost input value looks like about 1, and the rightmost is 6. That interval is going to be closed at 1, but open at 6. And similarly, the range goes from, looks like about 7 to, careful now, the top range value is up here where my cursor is. That looks like about 16. And it's going to be open at 7, closed at 16. So let's see if we got this one right. Did that again. There we go, right? So the range is, the domain rather, is from 1 to 6, closed at 1, open at 6. The range from 7 to 16, but open down at the bottom at 7 because of that open circle. Okay, so there's some more exercises that I've done here. I'll open those up in the notes that I post, but let's move on for now into section 1.3, which is, as you can see, about rates of change and behavior of graphs. So I'm going to start this with some data, excuse me. And what I have here is population data for the United States. And you can see I have a column of years and I have a column of populations in millions, and we stopped some 21 years ago. I think the population today is somewhere around 330 million. In any event, let's address some questions about this data that will lead us to this notion of rate of change. First question: which variable should we think of as the input and which variable is the output, right? We always try to model things in this course using functions. Functions have an input and an output. And we've seen a couple examples similar to this already that should cue you to the fact that the year is the input and the population is the output. So the input is the year, we'll call that T. The output is the population, so it makes sense to express the relationship P of T, right? So P is the name for our population function. And so what this model means is that if we were to evaluate P of 1980, that would give us the population in 1980 in millions, which in this case is just 227.2, right? So I suppose we can write that. Oops. There. Okay. All right. So now we understand our model a little bit. What was the population of the US in 1940? Very straightforward question. You don't even probably need to express the model to figure this out. We just go up to this row right here and can see that the population was 131.7 million. It's worth noting that we can express this in functional notation by writing P of 1940 is equal to 131.7. All right, so now the question that we're really interested in this section: how fast did the population grow from 1900 to 1950? So we do have information about those 2 years. There's 1900, there's 1950. However, the question that we can answer directly is, what is the population? Not how fast does the population grow. So we should think about this one a little bit. A couple of preliminary pieces of information. The population in 1900, well, that's easy enough to figure out, is 76 million. Now, this doesn't answer the question, but it looks like a relevant piece of information. So it's worth writing down that P of 1900 is 76. And similarly, the population in 1950, again, we can read that right off the table here, is 151.9. And again, in functional notation, that looks like this. Okay, again, neither one of these numbers is really the answer to the question, but it seems like they ought to be relevant. And indeed, we can tell from these two numbers how much the population grew, not necessarily how fast, at least not immediately, but how much. To figure that out, we just take the difference between the two, right? So how much did the population grow? Well, we just take the population in 1950 and we subtract the population in 1900. So the math here is straightforward, right? You can do that subtraction and I come out with 75.9 million. A little bit of notation and terminology. We'll call this quantity delta P. So delta often, this is a delta, that triangle is the Greek letter delta. This often gets read as change in whatever comes after it. So delta P is the change in P. And this is the change in population over a certain time interval. and we'll express the time interval using interval notation as we usually do. All right, well, now though we're getting close to being able to address this question of how fast. If the population grew by this many million people over a 50-year span, we can estimate how fast it grew by just dividing, right? That is, if I take the change in the population, that's the numerator here, and I divide by the number of years, which is 50, then I get what we'll call the average rate of change of population over time. Now notice a couple of things. First of all, so we can get rid of that silly A at the beginning here. If I backtrack the calculation to the beginning, what I've done is I've taken the population in 1950, I've subtracted the population in 1900, and I divide by the difference between those input values. That is, what I'm computing is the change in the output, delta P, divided by the change in the input, delta T. And that's how we'll define average rate of change, right? Change in output divided by change in input. So generically speaking, if we sort of get a little abstract here, if y is a function of x, then the way I get average rate of change is I take the change in the output and I divide by the change in the input. And so in theory, I can compute this over any input interval, I think. And the units of this quantity, it's worth mentioning, are output units per input unit. So in our example up here, the units are million people per year because the outputs here are measured in millions of people and the inputs are measured in years. So I'll use this abbreviation AROC to stand for average rate of change. That's just an acronym. So the average rate of change of population over the interval, let's do one over a different interval just to do the calculation a little bit more quickly. Well, I need to compute change in population over change in time, right? Delta P over delta T. So I take the population at the end of the interval minus the population at the beginning of the interval, divided by the change in the input over the interval, which is just the difference between the two endpoints. And so from here, it's mostly calculation, right? These values in the numerator, P of 1900, I can get from this table, right? Here's P of 1900 is 76. I guess we did that one before. And P of 1870 is right here, right? 39.8. And then once you have this, it's just plugging into a calculator and we come out with 1.207 million people per year. So the interpretation of this is in this interval, the population grew on average by 1.207 million people per year. Of course, the population grows in fits and starts. It's not the case that it grew by this many every year, but that's the average rate of change over the interval. Okay, so from a graph, let's say, so here what we did was we started with an input-output table, basically. This table is an input-output table, and we calculated average rate of change from the table. What if I have a graph of a function, right? This is one of the three major ways of expressing a function. We can use an input-output table, a graph, or an algebraic formula. So how do I get the average rate of change here over, say, the interval from 2 to 4? Now notice whenever we ask a question like that, that 2, 4 is an input interval, right? That's how we structure this communication, average rate of change over 2, 4. So that's the interval from this input where the cursor is to this input right here, right? The inputs are on the horizontal axis. And I do the calculation in much the same way, right? It's change in output over change in input. So I take the output at the right end of the interval, and you can see that's about 10, right? Outputs are on the vertical axis, minus the output at the beginning of the intervals, the output at 2. Now be careful, this vertical scale here, where the axes cross is not at 0, 0. You can see that this is not the full 10 units. This looks like it's about 5 or 6. I guess we'll call it 6. And then I divide by the width of the interval, 4 minus 2, and then it's all calculation from there. And I come out with an answer of 2. Okay, so this is just what I verbalized a moment ago. There are no units here because this function is just kind of an abstract graph. The variables don't measure anything. So what if we have a function formula? What if I have something like, here's a function, f of x equals x plus 3 times the square root of x, and I want to find the average rate of change of this function over some interval of inputs. Again, it's always the same idea. I do change in output divided by change in input, right? Delta y divided by delta x. And the way I get change in output is I take the output at the right end of the interval minus the output at the left end of the interval. If I have a formula for the function, then the output at the right end of the interval is f of 9, and I compute that by plugging into the function. I bet that's what's done down here. Let's see. Indeed, right? So f of 9, I just plug 9 into my formula in the input slot. I get 9 plus 3 times the square root of 9. That comes out to 18. And when I evaluate f of 1, the function at the left end of the interval, I get 1 plus 3 times the square root of 1. That comes out to be 4. So that's where the 18 minus 4 in the numerator comes from. And the change in the input is much easier to see, right? From if the input interval is from 1 to 9, then the change in the input is 9 minus 1, which is just 8. All right, so when you do the math, we get a result of 7/4 or 1.75 is the average rate of change here. Okay, so here's another average rate of change from table example. Again, I will open this up in the notes, but let's go ahead and move on since we have done a couple of these examples already. So again, I'll open these up in the notes so that you can read them over, but we've talked about calculating average rate of change from a table and average rate of change from a formula already. A couple of other notions that I want to talk about in this section. First is the notion of a function being increasing. This is visually very intuitive. Here's a graph of a function that is increasing. And what that means visually is that as I go from left to right, the graph runs uphill, right? So if you go from left to right in the inputs, the outputs are going up, right? That's what it means to be increasing. Technically, it means that if you take two inputs and they are in order, then the outputs are in the same order, but I think the visual definition is a little easier to grasp. The key connection here is that the average rate of change of an increasing function is positive, right? That is, if you take any interval in this graph range, the second output will always be bigger than the first output. So in that fraction, in that delta y over delta x fraction, top and bottom will always both be positive. Okay, and then decreasing is just kind of the flip side, right? Here's a graph that is decreasing. And what that means is as I go from left to right on the graph, as the inputs increase, the graph runs downhill, right? That is, the output values decrease. And the connection with average rate of change is that now average rate of change is negative. Because if I take any input interval here whatsoever, the second output will always be lower than the first output, which means that when you do this calculation for delta y, you're always going to get a negative number. The denominator here will always be positive, and negative over positive is negative. Okay, and then the two more notions that I want to cover in this section, and then we'll stop the video. First, a point where a function changes from increasing to decreasing is called a local maximum. Again, visually, this makes very good sense, right? If you looked at this graph and I asked you, where do you think the local maximum is? Hopefully you would point to something like the purple point right here, because it's the highest output value. Technically, the way you get what's called a local maximum is a function goes from increasing on the left to decreasing on the right, and that forms a point like this that's kind of a peak point. It's called a local maximum because it's possible that if we go further out to the right, this function turns around and comes back up and gets bigger than that purple point. But at least this point is sort of the biggest in its locality, hence the name local maximum. And a local minimum is the flip side of this. Again, if I just showed you this graph and said, where's the local minimum? Hopefully you would point at that purple point right there. It's the lowest output value. But again, technically, a local minimum is where a function goes from decreasing to increasing, right? So over here on the left, average rates of change are negative. Over here on the right, average rates of change are positive. So here's a graph of a function that's a little more complicated. Let's talk a little bit about the sort of increasing and decreasing and local maximums and local minimums for this function. So the first thing I would note is that this function is increasing in two places, right? Over here on the left, it's running uphill where my cursor is going right now, but also over here on the right, it's running uphill. And then of course in here, it's running downhill, so it's not increasing in there. So it's increasing from here up to about this point. We'll always express increasing and decreasing using input intervals, right? So we'll ask for what inputs is the function increasing? Well, this input is maybe -1, -1.5. You can see this input right here is -2. We'll call it -1.5. It's just a visual estimate. And it stops increasing right about here, right? This is where it turns around and starts to go downhill. That looks like about x equals 1. So there is the first interval that it's increasing on. And then out here on the right, it starts increasing, I guess, about x equals 4. And then the graph stops at x equals 6. So we'll call this the interval from 4 to 6. As far as decreasing, well, it's decreasing from this point right here to this point right here. And again, we're going to express that as an input interval. The left-hand input is about 1, and the right-hand input is 4. And we should match this up with the values that we used in the first part of the example. So it's decreasing again on the interval from 1 to 4. As far as local maximums and local minimums are concerned, again, hopefully you look at this graph and say, so there's a local maximum where the cursor is now, and here's a local minimum where the cursor is now. And indeed, you can also detect this just from our intervals of increasing and decreasing, right? At the point x equals 1, it changes from increasing to decreasing. So that's a local maximum. And at the point x equals 4, it changes from decreasing to increasing. So that's a local minimum. And I believe that's what these last two cells say here. Indeed. And so how you express this, how you kind of report a local maximum, you can report the coordinates of the point, right? So this point right here looks like about the point 1, 10. I think it's almost better just to report the x value. And the reason is it's easy to confuse this point with an interval because of the notation, but either is fine. And likewise, the local minimum is this point, which looks like about 4, -15. Or if you just say a local minimum at x equals 4, that's fine as well. Okay, last thing that I want to mention real quickly in this section is the notion of a piecewise function, which I don't think we've talked about an example of before. Here's an example of a piecewise function. Boom, right there. And what makes a piecewise function is the fact that it has these pieces. And the idea is the way you evaluate this function depends upon the input, right? So for some functions, we have just a single input formula, like that one we did before. Where are you here? Right, where we just have a single formula for the function and we apply that formula to compute any output value. Here, when we try to compute a function value, first we're going to have to decide which rule to use. So for example, if we want to compute f of 0, the first thing I have to do is decide, well, which formula should I use? 3x minus 10, x squared plus 4, or just the constant -2? And of course, what we do is based on the input 0. 0 falls into this first category. It's less than 1. So I'm going to use this first rule, 3x minus 10, and that's what I plug into to evaluate f of 0. Similarly, if I want to evaluate f of 2, I have to decide which rule to use, and which rule to use depends on where the input is. 2 satisfies this second condition. Notice that these conditions on the right here should not overlap in order for this function to make any sense. So I use the second rule, x squared plus 4, and when I plug a 2 into that, I wind up with the output of 8. And finally, if I try to calculate, say, f of 8, 8 falls into this third range. It's greater than or equal to 4. So I just use the constant rule, -2. When you graph an when you graph a piecewise function, pardon me, you typically get something in pieces like this. So this is the graph of this piecewise function. You can see that these breaks here, this first break is at x equals 1, the second break is at x equals 4, because those are sort of the boundaries between the different rules. Don't worry too much about generating graphs like this. Just be aware that graphs of piecewise functions occur in pieces. The one thing I will say about specific functions and graphs is if you go to the text in the end of section 1.1, get there. Here we are. There's this little page with graphs of what they call toolkit functions. These are all sort of kind of very basic atomic functions, and it would be useful to familiarize yourself with these graphs. It's not really an issue of memorization in this course. This is a remote online class, so you're always going to be able to look things up. But if these are, in fact, in your toolkit, it will make your work faster and more efficient. This is on page 12 of the textbook. Okay, so that's good for sections 1.2 and 1.3.